Hi, I'm Mohammed, and along with my colleagues Rachel, Jrayu, Priyanka, and Kwang, we've used the skills learned in this course to tackle predictive policing challenges using the Toronto Police Major Crimes Indicator. The dataset consists roughly of 242,000 data points, which form over 210,000 police reports, filed within 2014 to 2021 by the Toronto Police. So along with spatial and temporal features, the dataset also reports the type of crimes included in each record, which consists of assaults, break and enter, auto theft, robbery, and thefts of high value. So we've incorporated the relevant steps of the end-to-end machine learning process, including exploratory analysis, data cleaning and preparation, visualization, ideation of business objectives and solutions, engineering features relevant to the objectives, to the objectives that I'm going to discuss, as well as ML modeling, as well as inference from the results. Okay, so here we can see a map of a small sample of crimes plotted onto Toronto, the map of Toronto, excuse me, as well as on the bottom right, we can see hues representing different types of crimes. And as is evident, predicting detecting any sort of pattern with a human eye is a near impossible task. So having said that, and given the cost of law enforcement, given that it's shouldered by Toronto taxpayers, it's incumbent that the Toronto Police Service, its $13.2 billion operating budget, be put to more efficient use. This can be done through more proactive policing, which is something the TPS is aiming to do. So the question arises, what makes efficient law enforcement? So without getting too philosophical, it's simply maintaining low crime at an optimal budget. This is easier said than done, but with ML, well, ML can help in allocating police resources, leading to cost efficiency and efficient proactive policing. Now, pursuant to that, our project aims to, one, predict crime hotspots given a neighborhood and specification, and two, predict the likeliest type of crime given location and time details. So we can see that there are benefits that accrue from this, which is that predicting hot crime zones in neighborhoods provided an area of focus. This provides an area of focus, for units that are assigned to patrol those neighborhoods. The TPS is also able to predict the likeliest type of crime given those spatial and temporal details. This would help prepare police divisions to deploy the right kinds of units, since it would normally be hard to enforce certain laws given the time of day, for example. While other crimes, for example, require specialized budgets for training officers, such as sexual assault and boat theft. Okay, so for objective one, we've opted for a regression to predict the X and Y coordinates of a crime, which represent the meter equivalent of the latitude and longitude coordinates. So they're a meter translation of the latitude and longitude degrees. So this prediction is done using a series of original and engineered features, as is evident here. Both spatial and temporal features, of course. And for some of those engineered features I was talking about, they consist of turning temporal features into other temporal features. So just to demonstrate one, and by the way, this is for the purpose of reducing overfitting. So to demonstrate that, we created a season feature to help normalize the day-to-day fluctuations of crime rates. This is the case for the other temporal features as well, as is evident from the slide. Also, with regards to encoding, most of our features we reckon they recur frequently as well as with them being categorical. So we decided to encode them all the input features, and then the target features were continuous X and Y predictions. So we didn't see it appropriate to encode them, so we just left them as is. However, we did use the meter versions of the latitude and longitude degrees, which helps us make a more meaningful estimate. Right, onto modeling. So for modeling, we follow the basic process of train test splits, pipeline creation, parameter optimization, training an ensemble learner, which is the voting regressor, as we'll see, and then finally reading errors as well as scoring our models. So looking at this, so the train test split was roughly 70 to 30 respectively. We also incorporated feature selection and the estimators of choice in our pipeline. We also ran a grid search to optimize the parameters, which were, So we had linear regression, elastic-net regression, XGBoost regressor. So those three, you could see the parameter grid over which they were optimized, as well as the resulting optimal parameters. So the results were rather impressive. The results were rather impressive, as we could see here. Most estimators yielded errors of around 1,000 to 1,100 meters for both training and data sets, with the exception of XGBoost regressor, as is evident here. So that showed greater standard deviation. As the next slide shows, in the third tick here, we could see that it has a greater standard deviation. And that's also demonstrated by the learning curves with it be taking longer for the XGBoost regressor to converge in terms of training and validation relative to the other two. Okay, going back for a second. So the voting regressor was also used to aggregate the linear, elastic, and XGBoost regressors and did evidently improve their performance. Okay. So what does this mean in practice? To demonstrate using outdoor assaults, they tend to be the highest crime type reported and hence require a large resource allocation. So neighborhoods, for example, with higher population densities feature higher indoor assaults due to the prevalence of condos and apartment buildings. On the other hand, outdoor assaults are more ambiguous given every neighborhood has a quote-unquote outdoors. So this makes them harder to anticipate and prepare for. So we can further look at the dangerous neighborhoods with comparable densities such as those here. And we can extend the analysis to look at predictions versus actual occurrence location of crimes based on season as well as the day of the week. And compare the relative distances as demonstrated here. We can even dig deeper and look at the waterfront community, for example, and look at the prediction performance in different seasons, given the same days of the week. What about the pandemic? So the pandemic, based on a random draw, the pandemic may have had an effect on predictions, although it's hard to conclude from a single observation, but a wider sample value. We can infer more valuable information if we were to have a wider sample. So given the error in the prediction of our model, given it averages to 1.1 kilometers roughly, or in terms of time, it's 5 minutes and a quarter, it can be used for units patrolling in cruisers, for example, and even those on bicycles, and arguably even those on foot. So in case of those on foot, one can set a benchmark for like fitness purposes, for example, in that running, you're required to run 7 a mile in 7 minutes and 2/3 of a minute, which what our model expects the error to be. So this only scratches the surface of our predictive model and of the possible use cases in practice. So with that, I let Kwang take over to explain the second objective.
For our objectives 2, we want to predict UCR code given details on location and time. UCR code is a specific code for crime type, while MCI is a generic label of that crime type. We selected only certain features that we think will be helpful for the prediction, grouped into location and time. In the process of cleaning data, we did label encoding for occurrence day of week and premises type because these attributes are provided as string, so we simply translate to a numeric value for an easier evaluation. Similarly to the previous objective, we selected 3 models, tuned parameters on them using research, and then did a soft voting trying to improve the performance of selected models. During our data analysis, we opt into choosing UCR code instead of MCI because there seems to be an extreme imbalance with MCI, while if we split into a subcategory of crime using UCR code, the imbalance was a little bit lifted. However, in the end, using the predicted UCR code, we can easily map into an MCI label with a simple lookup. We also dropped some of the rows when training with Stratified Shuffle Split at 5 folds. These are the rows that wouldn't appear more than 5 in the training dataset, making our split less balanced. This is the result of our training. We started with decision tree after doing research on a number of parameters and stratified split them 5 times. Our best model returns an accuracy score of 48% and F1 score of 41.5%. This is not particularly high for classification model, so our trajectory is to try different models and doing a soft voting to further improve the performance. Since then, we also decided to use accuracy score on a weighted average F1 score as a performance measurement for our model, so you see it being repeated. The next model we are tuning is the SGD model. While we also was able to do splitting, it takes a really long time to converge, even for 20% of our data only. And running a full dataset is not possible for us. Furthermore, this model performs really inconsistently and really poorly. The best accuracy score we had was only 28% at 90% F1 score. Moving on to the support vector classifier, this is the worst models we've chosen for this problem in terms of cost. We ran training multiple times without shuffling data and with increasingly smaller data set. After several attempts, it returns an accuracy score of 38% and 26% F1 score at only 5% of data being trained on. Given that training doesn't get better with different models, when doing voting, we opt into doing soft voting of own algorithms with a higher score for decision tree, hoping it will return better accuracy and F1. This voting was not also done on full data because it took us 3 hours just to get the result of 10% of our training, although we tested on the rest of our data at 90%. The final result was not what we expected. It's only 42% accuracy and 31% at F1. So for our short research, this particular classification problem, decision tree would outperform the rest of our chosen model even with voting. So we did another round of training with the best file params and full data, and this is the result: 47.9% accuracy and 41% F1 score. The cost of training is also almost instant, which gives us more confidence on continue using this model to make prediction. To make prediction, we had 10 data points using our best model to obtain the UCR code and map it to an MCI. As you can see, some of the prediction was fitted correctly. There are two types of wrong prediction. One is totally wrong UCR code and MCI type, and the other is a wrong UCR code, but the CRAM does belong to the same CRAM type. So for our conclusion for trying this classification problem is that our model selection is not good enough. It is costly in terms of training, time and resource, while doesn't yield a desirable outcome. However, we do hope that if someone is to use these models, it'd be helpful to have a little understanding of the future, which type of crime is going to happen, and maybe be prepared for that type of crime properly. Given a mean distance error, the model that predicts location of crime could be a solution. And if we have a better prediction on the crime type, we can only rely on the information to prepare for a certain type of crime that's about to happen. So you don't want to bring a knife to a gunfight. Of course, the best scenario is that a crime doesn't happen. So it might be next to impossible to predict if a crime doesn't happen was because of our direct result of our prediction, or was because of we were super wrong about that prediction. So this concludes the end of our presentations. We apologize for not making it in class, but hopefully this video recording provides a good enough representation of what we've worked on as a team for the last month. Each and every one of us has contributed to make this happen, and if you need further question discussion, please reach out to anyone on the team. Thank you for your time, and I hope we speak soon.